Okay, so now let me say something about how you can recursively construct the terms in the expansion for the modified vector field. So this is a recursive approach to backward error analysis. Okay, so let's assume that you know the modified vector field. Up to a certain order. So let's call that f tilde I. Okay, such that the numerical method, the one-step method, psi h is a discretization of order p is equal to I plus 1. Okay, for the modified equation, for the modified ODE. Okay, and of course, you know, any method is at least consistent, so that's at least first order. So you could imagine that you know, f tilde 0 is just the original vector field, right? So it's always possible to have sort of the initial, you know, it's like unmodified vector field. It's like as part of this recursive method. Okay, all right. So anyway, so we have this you know, modified vector field such that the numerical method is a discretization of up to order. It's like p equals to I plus 1. Okay, which is to say that dz dt equals to f tilde I z of h, right? Of this modified ODE, which basically means that, and if this is of order p equals I plus 1, that means that the exact flow of this modified vector field, right, minus the numerical method applied to the same data has an error term, has a local error term, which is big O of h to the I plus 2, right? That's the definition of the order. Okay, then what you can do is that we can define the next correction term, which I call delta fi plus 1 h, okay, of z, and this is equal to the limit as tau goes to 0 of the numerical method with time step tau applied to some initial data z minus the exact flow map of the f tilde I modified vector field with time step tau applied to the same data divided by tau to the I plus 2. Okay? And the reason, of course, is that you want to have the scaling, so you basically just want the leading order error term, and by sort of, you know, more or less dividing by h to the I plus 2, you just get the coefficient, if you will. Okay, so then by construction, okay, the numerical method psi h is a discretization of one higher order, of order p equals to I plus 2, right, with respect to a new modified vector field. F tilde I plus 1, okay, where f tilde I plus 1 is, of course, f tilde I plus basically h to the I plus 1 right? Delta fi plus 1, right? So, so that's basically what you need to do, okay? In order to get this next higher order term. Okay, and let's just see how that works. Okay. Okay. So let's try to prove that that's actually true. Okay. Okay. So what does it mean? It's like for this thing to be one higher order. So I have to look at the local truncation error. It's between the exact flow of this now f tilde I plus 1 term and the numerical method, right? So this is of course nothing more than the exact flow of the f tilde I term h plus h to the I plus 2 delta fi plus 1 of z. Okay, so this is just the linear correction factor, if you will, right? Plus something which is big O of h to the I plus 3 cubed. Okay, minus numerical one-step method. Okay, so this is of course nothing more than h to the I plus 2 delta fi plus 1 of z. Okay, plus the numerical flow, the exact flow of the f tilde I vector field minus the one-step method, right, plus something which is big O of h to the I. This delta fi plus 1, right, exactly so that it scales. So there's this h to the I plus 2 term, right? So if I divide across here, then I get exactly this expression here, more or less, divided by h to the I plus 2. So this term is going to have the same asymptotics. It's like as this term here, and so they'll cancel out basically. Okay, so all you're left with is big O of h to the I plus 3. Okay, and again, it's because essentially it's like by the definition of delta fi plus 1, it's like given here, this term will be cancelled out by this term. Okay, and the limit as h goes to 0. Okay, all right, so that's just sort of a simple calculation, and then that tells you that now the truncation error is big O of h to plus 3, which means that the order to which the numerical method approximates this exact flow is order, it's like I plus 2, right, which is exactly what we're trying to show. Okay. All right, so, and as I sort of said before, it's like this recursion, it's like starts with the original vector field, right? So the remark is that the recursion starts with f tilde 0, which is just f, right? And the other observation is that for a method of order p, the first p minus 1 vector fields sort of these perturbation vector fields, the delta fi vanish. Okay. All right. Okay. So the second remark is that the series does not converge in general. right? So it is not a convergent expansion, it's what's called an asymptotic expansion. Okay. All right. Then what you might ask, well, what happens if it is only asymptotically is only asymptotic expansion? Then what happens is the following: that when the maps are real analytic and bounded, right? It is possible to obtain estimates of the form. So the norm of the difference of these two maps, the flow map of the modified vector field and the one-step method, right, is less than or equal to some constant c1 h c2 I plus 1 h to the I plus 1, okay, where c1 and c2 are constants. I should say there's an fi here, right? Independent of the iteration index I, okay, and step size h. Okay, so more or less, it's like what that's telling you is that you have a estimate which tells you to what extent the exact flow of this f tilde I modified sort of vector field, it's like differs with the one-step method. Okay, and so you have some sort of estimate which depends on I, and then the art, if you will, is to choose the I so that that error is as small as possible. Okay. Okay, so what we have so far is that the difference between the numerical method, right, the one-step method, and the exact flow of the modified vector field has an estimate which looks like C1H C2 I plus 1 H I plus 1, and I guess this is the I modified vector field. Okay, so the optimal truncation for this asymptotic series occurs for I star is equal to the integer part of 1 over C2 EH minus 1. Okay, so let's call that S. Okay, this implies that C2 I star plus 1 times H is less than or equal to C2 S plus 1 H, which is e to the minus 1, and I star plus 1 is greater than S. Okay, so putting that together, it's like, and putting it back into this expression, what you get is that the difference again between the one-step method and the exact flow of this I modified vector field, okay, where I is sort of the truncation up to the ith term, is less than or equal to C1H. Okay, so I should do this for the optimally truncated vector field, right? So f tilde I star, okay, this is less than or equal to C1H e to the minus I star plus 1, okay, which of course is less than or equal to C1H e to the minus S, okay, and I can write this as, so this is less than or equal to 3 times C1H e to the minus gamma over H, where gamma is equal to 1 over C2e. Okay, so what happens then is that the modified differential equation is given by this optimally truncated vector field, right? dz dt is f tilde ch, and this is defined to be just this optimally truncated vector field. This is in contrast, it's like to what you would have gotten. It's like if you had done the standard forward error analysis, right? All right, so let's see what happens if you had done the standard forward error analysis. Okay, so using sort of the standard forward error analysis, right, the difference between the exact solution of the modified differential equation and the numerical solution is bounded by the following, right? So kappa e to the tn L bar minus 1, right, e to the minus gamma over h. Okay, so where kappa greater than 0 is a constant, and L bar is greater than 0 is the Lipschitz constant of the numerical method. I guess, okay, well, I guess what I should have said is that, okay, so this is essentially the truncation error, if you will. It's like associated with, this truncation error, it's like, if you will, associated with the, if replacing, it's like the exact solution of the optimally truncated modified vector field, it's like with the symplectic integrator, and then if you apply it, it's like the standard forward error analysis, like to this optimal truncation error, then you get this estimate here. Okay, so all right, so in contrast to sort of forward error analysis, with respect to the original differential equation, right, the error between the exact solution of this optimally truncated modified vector field and the symplectic integrator, right, has errors, it's like, which mean exponentially small over periods which are in some sense exponentially large. Okay. Over exponentially long time intervals. Okay, so if your time is less than gamma over h of bar. Well, sorry, this is not over exponentially long times. This is just over long times. Okay. Okay, and then often this time interval is not long enough. So sort of more sophisticated methods such as shadowing have to be used in addition to backward error analysis. All right, so again, to recap, it's like what this result is basically saying then is that if you do this optimal truncation of the modified Hamiltonian, then what happens, actually, if you're doing optimal truncation, it's like of the modified vector field, right? Then what will happen is that the error between the numerical method and the exact flow, it's like of that modified, optimally truncated modified vector field is going to be, it's like given by this expression. And if you recall, it's like this has to do with the fact that you have a term, it's like which depends on the sort of the local error, right? And then there's this sort of exponentially increasing, it's like a constant, which depends on the length of the time interval which you're integrating over. All right, so let me just stop here.